Hey guys, today I'll be showing you a Vpython simulation of a bouncing ball. This is how the simulation will look like. We will see a ball bouncing under the influence of air drag, and at the same time, we will see a graph of its speed versus time. So, first of all, we will start our program by writing this from Vpython import, and we will introduce several physical constants, including the air drag constant, 0.9. And then we will set up the scene, the floor, and the ball, which is basically the same as the last time, so I will not go into details. The ball's initial position will be set at minus negative 15 size, which is its radius, 0. And its initial velocity will be a trigonometric function, which the theta we will set at 1/4 pi. And the time step for this while loop will be 0.001, and I'll run this loop at a rate of 1,000, so it will be running at the exact real-world time. And now for the ball's velocity, it is slightly different from the last time because this time we have to consider the air drag. So we can look at this line here. The ball's current velocity will be its previous velocity plus this is the acceleration caused by the gravitational force, which is 0 negative g 0 times the time. And then this part is the acceleration caused by the air drag. Because the acceleration caused by the air drag is proportional to the ball's velocity. That is, the faster the ball is traveling, the more air drag it's going to feel. So our acceleration of the air drag will just be the air drag constant, which is 0.9, multiply the ball's velocity, then multiplies the time step. And because the air drag is making the ball move slower instead of speeding it up, so the acceleration caused by the air drag will be negative. So there we have the ball's current velocity, its previous velocity, plus the acceleration under gravitational force, and the acceleration caused by the air drag, with a negative sign. And here you can see a different notation of the same equation. So these two equations are the same, it's just this notation will make it shorter and more precise. And the ball's position will be, these two are the same, so we can look at here. The ball's current position is its previous position plus the distance it traveled during this time. And we can write it as a plus equal notation. And right here, this if statement states that because in the end, I want to know where is the ball's highest height. So in the beginning, I will set its highest to its vertical position, which is its size. And every time that I yield a new vertical position, I will compare it to this highest, which is still its previous vertical position. And if the new y position is bigger, then I will change the highest to its current vertical position. So this means like after 0.001 second, if my new vertical position is bigger, then my highest will be this one. So if the ball is going up, the highest will keep changing until it has reached its highest, and then the ball will start to go down. And as the ball is going down, this condition will no longer be true, so the highest will not be changed. So the highest height will remain at its highest point. This is how I'm going to yield the highest height. And the if statement here will make the ball bounces. So if and and means that both conditions, this one and this one, has to be true for the program to run through the statements. So the first condition is if the vertical position is smaller or equal to the size, which is exactly when the ball hits the ground. And if the ball's vertical position is smaller than 0. So in our simulation, we assume that positive is upward. So if the vertical velocity is smaller than 0, it means the ball is going downward. So if this is true, if the ball hits the ground and its velocity is pointing downward, I will assign its vertical velocity to be the negative of its previous vertical velocity. This is because we assume that the ball bouncing motion right here is an elastic collision. And for any elastic collision, the magnitude of the velocity will not change. The only difference will be the position for the velocity. The direction of the velocity. So the negative sign means the magnitude will not change, but the direction will be the opposite, from pointing downward to pointing upward. So this is how the ball will bounce. And this n is n plus 1. This is because I want the ball to stop at exactly the third time it hits the ground. But I have no idea when the ball is going to hit the ground for the third time. So in the beginning, I will assign n to 0, meaning that the ball hasn't hit the ground for any time. And while n is smaller than 3, we'll go back to this later. So if the ball hits the ground and if it bounces for the first time, my n will increase by 1. So now my n will be 1, indicating that a ball has hit the ground for 1 time. And because n is still smaller than 3, so the while loop will run again. And then it will hit the ground for the second time, it will bounces for the second time, and now my n will change to 2. And then the while loop will be run through again. Then here comes the third time. The ball hit the ground, its velocity is pointing downward, so it is ready to bounce, and the n is increased to 3. But just as it is going to bounce back for the third time, the condition for the while loop no longer is true. Because n is 3, this condition is false. So the program will exit the while loop, and the ball will stop exactly when it touches the ground for the third time. So this is what the n is doing. And in the end, I will calculate the ball's displacement and print out its distance and the highest height. So now, this is how the simulation looks like. 1, 2, and 3. Okay. And finally, I want to add a graph. So I will name a graph oscillation. And here, a line to the right, it just means that it will appear at the right side of the screen. So I add a line attribute to the scene as well, a line to the left. And the function here is what I will do with a curve. So we're going to draw out the curve. It belongs to the graph named oscillation. The curve will be blue, and the width is just the thickness of the line. And because the function will be the t and the x-axis and the ball's speed on the y-axis, so the x-axis will just be the time, and the speed is just the magnitude of the velocity. So this will be the y-axis, and this is just how simple it is. So right now, this is what the simulation looked like. The speed here and the time here as the ball bounces for the third time.